I will start with a little overview, trying to answer the three questions that you see on this first slide. So the first question is, do defects matter at all for high efficiency perovskite solar cells? Then the second one would be, where are they in space? So bulk versus surface. And the third question, by far the most difficult one, I think, is where are they in energy? Yeah, so where in the band gap are these defects? And to answer the first question, whether they matter at all, I want to just briefly say what defects are doing in perovskite solar cells and in any other solar cell. They're accelerating recombination via this Shockley-Rittal mechanism that you see on the right side of this panel. Shockley-Rittal recombination does essentially two things. It reduces the amount of luminescence that you would see, say in a photoluminescence or electroluminescence experiment. And at the same time, it reduces the open circuit voltage of your solar cell. And what you can do is you can, for instance, plot the open circuit voltage of many solar cells as a function of their band gap, which you see on the left side of this graph. And what you will note is that you cannot see any points that are above this blue line here that says 10 to the minus 1. Yeah, so that's the 10% luminescence quantum efficiency line. And that means that all the high efficiency solar cells that we have so far have less than 10% luminescence, external luminescence quantum efficiency. And that means still more than 90% of the electron hole pairs will eventually create heat at open circuits. So defects are indeed still an important aspect, even for high efficiency solar cells. And you can also look at the development of these losses as a function of time. So this graph shows on the x-axis lots of different, at that time, high efficiency perovskite solar cells with a year attached, and at the end, silicon and gallium arsenide record cells. And on the y-axis, you see the percentage of the so-called Shockley-Queisser efficiency of these devices. So the first one was a 15% solar cell, and that meant it had a bit less than 50% of the efficiency that it could have, which is about 30%. Yeah. And what you see here are green, red, and yellow bars, which indicate the losses in the different, say, disciplines, like losses in fill factor, BOC, and NJC relative to the Shockley-Queisser limit for that respective band gap. And when you just look at the green bars, you can see the development in the losses in open circuit voltage. And they indeed go down over time, especially the last one here from Jingbi Yu's group last year was a substantial improvement. So the green bar is quite small. It's also smaller than the one in silicon, which is obviously limited by Auger recombination. But it's still not as small as the one in gallium arsenide. So there's still some losses left. Okay, so next question would be, after we've answered the first one with a yes, would be, where are they in space? And with that, I mean, are they predominantly at the surface or at interfaces within the perovskite, or is it more the bulk material that matters? And what you may have noticed yourself, if you've ever measured photoluminescence, transient photoluminescence spectra as a function of time, usually perovskite on glass, or ideally passivated perovskite films on glass, they have often quite long lifetimes in the hundreds of nanoseconds or even microseconds. But whenever you attach contacts, so electron or hole transport layers to your samples, usually you get a substantially faster decay of the luminescence, which indicates that indeed there is recombination at these interfaces, and indeed that recombination matters. And in order to understand whether it always matters, it's helpful to look at a large range of materials and interface materials. And a nice study was done by my friends and colleagues in Potsdam, Martin Stolterfohr and his colleagues in Dieter Neyer's group. And what they did is they essentially measured the steady state photoluminescence of a whole lot of different perovskites with either an electron or hole transport layer attached. In this case, it was a triple cation perovskite, and you see from the total amount of luminescence that you get, you can determine the quasi-Fermi level splitting. And every order of magnitude that you lose in luminescence will mean KT-ln10, so 60 millivolt loss in open circuit voltage or quasi-Fermi level splitting of these samples. And what you see here is that each of the hole transport layers and each of the electron transport layers does indeed reduce the luminescence by, in some cases higher, in some cases lower amounts. That means that the recombination at these interfaces is indeed an important aspect, maybe in most cases more important than the one in the bulk. On this kind of analysis, there you can also find a poster later from the group from Max Kirchartz and the group in Potsdam that is a little bit of an extension of this general concept of using photoluminescence, but then is also applied to looking at the fill factor of these devices. Okay, so in terms of where are they in space, I would say mostly at interfaces. This is the most important aspect. This may be partly also due to band offsets that exist at these interfaces, but nevertheless, the defects there will then be more important than the one in the bulk. And in some cases, it may still be bulk recombination that matters, but it's essentially a question that has to be answered for every individual perovskite composition or way of making the perovskite. Okay, the third question will be, where are they in energy? So are they very deep? Are they mid-gap defects, or are they rather shallow defects? And this is a very difficult question to answer. And the reason why it is difficult is that it is so difficult to measure defect densities as a function of the energy and energetic position of these defects. So there was a few days ago, there was a paper coming out in Science, which used a method that's called DLCP, drive level capacitance profiling, to look at concentrations of defects. There would be a lot to discuss about the method, but I don't have time really to do that within the 15-minute talk. But I just want to give it as an example of one of the few methods that actually try to determine the depth of a defect. And what you can see here, that would be a density of states, and that would be energetic position relative to either conduction or valence band edge, which you don't really know. And you can see that this is a relatively small range of energy that you can access with this method. If you're generally interested in these types of frequency and temperature dependent methods to determine trap densities, there's also a poster I've seen from Germana Garcia Belmonte on the validity of these methods. Okay, so what we take from here, it's difficult to measure where they are, and even if we can measure it, it would only be a small slice of the band gap that we would be able to access most of the time. So another question that we can ask ourselves, okay, we don't know exactly where the defects are, but can we understand how detrimental the defects would be? Yeah. So if you usually look into the theory of recombination via defects, then the first thing you may see would be the equation for Shockley-Rittal recombination, which essentially contains these little lifetimes tau n and tau p, which are again dependent on essentially two parameters. One is the defect density, so higher defect density, faster recombination. But there's always a prefactor that I call Kn or Kp here, which essentially tells you how fast a single recombination event would happen. And now the question is, so how fast would transitions be in essentially any semiconductor? And for that, to answer that, the Shockley-Rittal theory doesn't help you at all. You need to go to another theory to really understand where the Kns and Kps come from. And what people do that try to calculate recombination coefficients or capture cross sections is they go to a picture of these transitions that looks like the one on the left, which has a y-axis that says total energy. So it's the energy of the electron plus the lattice. And on the x-axis, it has a one-dimensional configuration coordinate in most of the cases. So the configuration coordinate could be something like a bond length or a position of a defect atom in a lattice. And essentially for recombination to happen, so for this electron to recombine, first has to go to this defect and then it has to go down to the ground state. And for that to happen, this electron first has to essentially tunnel into a vibrationally excited state of this defect. Yeah? So it has to first go here. And then once it's in the defect, it has to tunnel into a vibrationally excited state of the ground state. And without going into too much detail, these transitions depend a lot on the distance, the distance between the defect level and the position of the electron here in the conduction band, and on that distance as a function or in relation to the energy of a single phonon. Yeah? And in perovskites, one of the important things is perovskites consist of very heavy atoms, so lead is heavy, iodine is heavy, and that means that the phonon energies are very small, which is normal for heavy or semiconductors based on relatively heavy elements. And the phonon energies, you find different numbers, but they're roughly all round about 1/100th of the band gap. Yeah? So 16 millielectron volt is 1/100th of the band gap, roughly. And that means even if you had a defect that is exactly in the middle of the band gap, in that simple theory with parabolic potential energy surfaces, you would then expect that you need 50 phonons for that transition and 50 phonons for that transition. And that would make these transitions not particularly likely. And if you now move a defect out of the middle, so let's move it, for instance, up to this region here, where that's the slice that the science paper would be able to access defects in principle, then we would see that it's closer to the conduction band. So the Kn capture for electrons would in principle be high in that theory, but the capture coefficient for holes would be that low that in total recombination would be quite inefficient. So based on that simple theory with parabolic potential energy surface and harmonic oscillators, essentially would expect recombination to be only efficient if you're very, very deep. Yeah? But that is essentially a preliminary result, because at some point one has to calculate really how the potential energy surfaces of practical defects look like. Now this principle would be quite good news, because you may know this diagram about defect tolerant, defect intolerant semiconductors. So because of the antibonding valence band maximum of lead-halide perovskites, many of the intrinsic defects would be rather shallow defects and not particularly deep defects. So that would in principle go together well with low phonon energies. But that's only, as I said, a preliminary finding. So what you see here is essentially a summary. So these are the capture cross-sections, and this is what, when you put the whole thing into Shockley-Ritz-Hall theory, then this is the effective lifetime that you would get. And that would mean if you put a defect here, you would get something in the hundreds of nanoseconds, but if you move it away from mid-gap, it would quickly be substantially less efficient in accelerating recombination. It's for a defect density as an example of 10 to the 15. Okay, so as a conclusion, defects do matter still, even in high efficiency perovskite solar cells. So that's clearly a yes. Where are they in space? I would say mostly at interfaces, but in some cases the interfaces may be that good that it's also the bulk that matters. And where are they in energy? At the moment, I don't know. The only thing I can say is that it's very difficult to measure, and that relatively simple theory of multiphonon recombination would predict that for such a material, the deepest defect should be a lot more efficient in accelerating recombination than anything that is shallow. Okay, thank you very much. So lots of people who helped me in the past.